play. Yeah, there we go. All right, so last time I fat fingered it and I put 7,000 instead of 4,000, so I crossed it out. And like I said before, even after working the problem, it was pretty wimpy problem. So I'm going to work through it so you guys can see how I did it, and then I'm going to change the weight to make it.
You change the depth of the weight.
I'm going to change
I want
the
to
weight.
change the depth.
We haven't gone over Boyle's law yet. That's today. So I didn't really want to get too far into Boyle's law yet. I just wanted to give a basic round up on the cylinder to take care of that. This was just a Archimedes principle type of thing. That's why I gave such a shallow depth this time. Next time we'll do Boyle's law calculation, and then you'll have to step it down to the depth and expand the gas to compensate for it. But that's a good point. That's what we're going to get into today. All right, so a couple assumptions that you're going to have to make. This is my little symbol for assumptions. If you want to steal it, you know, to help yourself work through the problems, go ahead and do it. All right, so 1 foot is approximately 1,728 cubic inches. I'm writing with a mouse, so it's not going to be as nice as my mouse pen. 1,728 cubic inches. If you can't remember that, Google's always a thing too. Another thumb rule is 1 gallon of salt water.
So wait, 1 foot is 720.
One cubic foot. Sorry, 1 cubic foot is 1,728 cubic inches. So sorry about that.
Okay.
Yeah, 1 cubic foot. Good catch. 1 gallon of salt water. We'll go gallon of salt water is 8.6 pounds on Earth. And we're not diving anywhere else, so, and that's the average. You know, it varies based upon you know, salinity, which varies where you are. You know, we're going to go 8.6 pounds. And then another one is 1 cubic foot of displaced water. So 1 foot of air, if you will. Will lift 64 pounds. And you know, it's a lot of air if you think about it. All right, so those are 3 good variables to use to kind of memorize, or you know, write down somewhere so they're in your notes. So those are good ones to remember. All right, you remember any of this, Zach?
No, I never actually. Wait, is my mic on? Yeah. I never got to any of the advanced dive sciences or anything like that.
Oh, perfect. Awesome.
Yeah.
Good. So this is new to you. That's great. So these are good thumb rules to know. Okay.
Okay.
All right. So the first thing we're going to do is get rid of this pesky, useless variable here. And you could do all this in one big step with some railroad tracks, you know, like, whoa, I didn't mean to do that. Stop it, let go. What's going on? Okay. I don't know why that happened. All right, you could do this with like big pesky railroad tracks, lots of units and stuff like that. And I like to do that if, you know, I'm really just trying to do it in all one big step, but I don't want to really do that. All right, but the first step I'm trying to do is, remember, I want to make this outboard engine neutral, right? So in order to find out, to make it neutral, 1, I need to find out if it's sinking or it's floating. And 2, which I presume it's going to sink. And then 2, I need to add air to it to displace the amount of negative buoyancy. So let's first get rid of this pesky, useless unit, because I don't use really any of that because this is my answer right here. This is what I'm going to need to figure out how much air I'm going to need to displace it with, right? So let's go ahead and do this real quick. And my end unit I'm going to need is feet, so that's going to be on the top. So 1 cubic foot is 1,728 inches cubed. And on the top is I have 4,528 cubic inches cubed. And if I bring up my calculator, oh, it's big. You probably can't see it, but you could do your own math too on your calculator and back me up on that in case I fat finger something. I have.
But so why do you put the 4528 on the right-hand side there? Like,
This is
why do we care about going from inches to feet or feet to inches?
because my thumb rules are I need cubic feet to pounds, right? This is what I'm going to be using to figure out how many pounds it displaces.
Right. Oh, well, yeah. Well, cubic feet to pounds. Again, I don't understand why inches come into play.
Because so back when we were making this this problem, we got this number from the fictional technical manual that said when we opened it up, we were like, oh, sweet, the engine tech manual says it gave us the displacement in cubic inches. Right.
Oh, okay. So we're just based on the tech manual, we're going on with what it displaces in inches.
Right. And the amount of water it displaced in inches is what the tech manual gave us.
Okay. Gotcha. Yeah.
So we're just doing a simple unit conversion from cubic inches to cubic feet. Right. So this where my thing go? If I did this real quick, it'd just be approximately 2.6 cubic feet. And if you think about like the size of an outboard engine, that makes sense. It looks like it's about 2.6 cubic feet if you consider it, filling up with water on the inside and stuff like that. Okay, so I'm really not using any of this stuff. Doesn't really come into play. I just wrote it down there because it's, I just write down all the assumptions that I know about stuff. So, but I will be using this.
Is that number 2 feet or inches?
Where? Right here?
On the far right-hand side where it has equal to.
It's 2.6 cubic feet. I zoomed out. I can see. Is it off your screen?
Yeah, it's off my screen.
Okay.
Oh yeah, I see. I see it now. I scrolled over. 2.6. Yeah, cubic
feet. And I'll bring it down here so everybody can see. 2.6 cubic feet. Okay, that's what I rolled forward. That's how much water the outboard engine displaces. So outboard engine displacement in cubic foot. Okay. Now I didn't see how much weight that water weighs, because if it is less than the amount of the weight of the engine itself, I know that it sinks. If it was more, then I know it would float. Right, so now it's pretty simple. I need to figure out the pounds in the front and the top, so it's 64 pounds per cubic foot. And I have 2.6 cubic foot to deal with. It's pretty simple unit conversions. The feet go away. Right, inches went away up here. All you have left is the pounds, units on the top, right here and right here. So just ignore that right there. Okay, so now it's just 64 times 2.6. bring up that again.
You need 136 pounds.
136 pounds. 136 pounds, right? Which is less than 170. Okay, so I know it'll sink. Let me double check that math real quick on mine, just because I can double check things. 64 times 2.6 equals, I got 166.4. Anybody else get anything different?
No, you're right.
Okay, so 166.4. I'm just going to round that down to 166. Right, and this is why I said it was a wimpy problem, because this is saying that it's 4 pounds negative. So 170. Don't forget units here. Pounds, right? So 170 minus 166 equals 4. And this number is positive, so it's backwards. So it's 4 pounds negatively buoyant. 4 pounds. I told you, honey, I'm teaching. Oh, that's a really awesome tattoo. 4 pounds negatively buoyant. All right, so if I use, so these were pretty wimpy numbers. So I would need a 4 pound lift bag in order to make this neutrally buoyant. So if I needed a 4 pound lift bag, and I know that water weighs 64 pounds, right? So I would go 64 pounds and 1 cubic foot per cubic foot. And I know I need 4 pounds to lift it. Right, that way those cross out, and all I have left is on the top is cubic feet. Then I would need, do the math, it ends up being 0.00625, which is like, I think like an eighth or something, like, which is 8 cubic feet, which is nothing, right? So I gave you some really crappy variables to deal with, you know, so
basically what you're saying is you could lift a 170 pound engine off of the ground with basically the lift bag we go diving with.
oh yeah, because it displaces so much water.
Interesting.
Right, yeah, because it's, I mean, that's how boats float, right? They may be heavy and stuff like that, but because they displace so much water that they weigh more than, or the water that they displace weighs more than what they weigh, so they
float.
That's buoyant. That's Archimedes' law in a nutshell, right? But let's I have an eraser on this thing.
So honestly, you wouldn't even take a second tank down with you at 20 feet.
Not on
You would
this
just
one.
use your,
No.
you would just use your secondary.
I would grab my smallest lift bag and some rigging, and I'd just put a little bit of air in my, and now it's going to be a little bit more. I mean, you could double this, right? Because, you know, if you doubled it, you're going to go to 3 or 2 atmospheres, right? You're still going to be at like
So you're 66 feet.
Yeah, you're no, 33 feet would be 2 atmospheres, right?
Okay.
You're still, you know, really conservative because you're going to only 20 feet. You're still, you know, 12 feet short of the 2 atmospheres, and you're still going to have plenty of gas in your cylinder, right?
So to answer the first question, you wouldn't need a secondary cylinder to bring down with you.
No, this was these were bad examples, right? So let's change some of the variables real quick. Let's see if I can change that. Okay, so now let's can I my eraser?
Let's use a bronze. Say we wanted to lift up the bronze propeller that's on the tugboat.
Let me just change the variables for this one. How do I erase? There's no erasers. How do I just do this? Okay, let's go back a little bit. That's all I can go back. All right, let's go. Okay, this is good enough. All right, let's, instead of this, let's say this is now 470. 470 instead of 170. Okay, now this is where it can get a little bit better. All right, where did the 60? So I have 64 pounds. This is still all the same, right? Per
Right.
1 cubic foot. And at this point, we're trying to figure out how much water, again, this thing displaces. Not any different than we did before. All right, 64 pounds per 1 cubic foot. And let's see, what were we in? It displaces 2.6 cubic feet. And this came to, what was it, 166 pounds.
Oh, 166.4.
Yeah, we're just gonna round up, we're just gonna round to 166. Now, this is where it would make the difference, okay? If this thing now weighed 470 pounds instead of, so we were 470 pounds minus 166 pounds. Whoops. Now let's do that math real quick. Now it's 304 pounds negatively buoyant. Now that's a little different, right? That's a lot more weight to lift, okay? So now we got to figure out how much air I would need, how many cubic feet of air I would need to displace that much weight. And you use this guy over here for that. Oops, you guys still see everything?
Yep.
I went full screen and I didn't mean to. All right, let me move this over here. So it's not my way. All right. Okay, so now it's, again, we're using this guy. All right, so it's we need cubic feet, so that's going to go on the top. So it's 1 cubic foot
64 pounds.
4 pounds. And then it's 304 pounds.
Why did you do the math where you have like multiple fractions like that?
That's called unit analysis. And it's the way I like to do math, because
Okay.
then, as long as it's simple multiplication and division, all you got to do is put the unit that you want and the on the end on top, and then you just go to town. You don't have to worry about like remembering, like, you know, what do I have to do? Do I have to multiply, or do I have to divide in this situation? All you have to do is remember to put the unit that you want on top and the unit you don't want on the bottom, and remember the simple ratios that you want up here, and then it's just unit conversions. That's all it is. If you have something that have like exponential stuff in there, this doesn't work. But if it's just simple multiplication and division, this works great every time.
Okay.
So you could do this you could have done all this problem in one big, we call these railroad tracks. You could have done it all in one big row, right? If you knew where you were going, but that kind of confuses people sometimes. So I just do it in step by step. So I could show that to you later if you want, if we have time. But anyway, so pounds. So it's 304 divided by 64. So I can't. Okay, there we go. 304 divided by 64. Oops, divided by
4.75.
So we'll round that up. Wait, oh, it's 46. 4.75.
Mhm.
So we're gonna go, 4.75 cubic feet. So 4.75 cubic feet of air I would need. So I need like a 5-pound lift bag. Would be a little, and if I wanted to be a little bit better, probably go with a 10-pound lift bag. I'd have to, let's see, let me Google it and see what's available. Right, but I need at least a 5-pound lift bag to get that thing neutral. Right, and that would be pushing it. So what kind of bottle would I want to bring down? Well, we could Google it and see what type of lift bags are out there, or what type of cylinders are out there. I don't know, type in Tony bottle.
Yeah, like the 19.
Well, let's see. They have a. Let's see. What's this small guy right here? There's a 6 cubic foot Tony bottle right here. That'd probably be the one I want to bring down. But we could calculate that later. Maybe not a 6, just to be sure. We probably want to bring up the next one, which would be like maybe a 13, maybe a little bit overkill, right? But we're going to calculate that on the next one if we were taking it down to deeper depths because of Boyle's law, which is this next exercise. I try to keep it pretty shallow. Maybe I should say this is 10 feet, so that depth was pretty negligible, but I'm trying to keep it fairly shallow. This is not quite one whole atmosphere. It's like 20/33, whatever that is, of an additional atmosphere. But you guys get the idea. So
Yeah.
zoom out on that. So that's that. Any questions about this and how I got all that stuff?
And in this case, you wouldn't really have to be worrying about like letting air out. Like once we get into Boyle's, and I always want to say Brunelli because I took aviation, so I just want to talk about Brunelli's theories on lift when we talk about lifting things, because I don't know. So you want to be like letting air out of the bag. Once we start getting into Boyle's theory, as you're going up, we're going to start having to let air out of the bag a little bit to equalize.
It depends what you're trying to do, right? Safety wise, if you are trying to bring this outboard engine, this says Mercury. It's my outboard engine, right? If you're trying to bring this outboard engine up in a controlled fashion, then yeah, even remember your biggest change in depth per change in foot happens in that last 15 feet. And we'll show that here in Boyle's law section. But that's why it's so hard to stay down and like steady at 15 feet during your end of your safety stop. Where at you're like 100 feet, maintaining depth is super easy, right? Because a change in depth, it's shallow depths, is a much larger change in like bubble compression or wetsuit compression than it is at 100 feet.
Gotcha.
Change in pressure due to a change in depth is much greater up here than it is at like 100 feet.
Gotcha.
So,
okay.
All right, cool. Any questions of that? Zach, you got anything?
No, I'm good.
All right, Chris, you got anything?
No, I'm getting it.
Cool. All right, let's go to share a different screen. And I gotta share, which one is it? Where'd it go? That one.
Well, there's one last question.
Yeah.
That those algorithms that you put together, 1 foot equals 7,208 8 inches, square, cubed.
Mhm.
Those things we should probably just have memorized.
You don't have to. You can always Google it.
Yeah, well, if you're on a boat and you're out in the middle of nowhere,
Yeah.
kind
I
of
mean, if
good
you're-
math to just to
if
have in
you're
your
on
head.
a boat and you're gonna go lift something like this, you're probably already planned it ahead of time. Like you're not gonna
Okay.
be mathing this crap on a boat. You're already gonna know I need this size of lift bag and I'm bringing this pony bottle out with me.
Okay, gotcha.
You're already gonna know all that stuff.
So you're gonna do all that on shore, then go out there and then try to execute the plan.
Yeah, you're not gonna be planning this stuff on a boat unless you're on like a big expedition boat and you guys are out there for days and you're looking for something specific, and then you go out there and you find something and you measure it and then you determine its alloy, and then you go up there with a bunch of engineers and you determine the weight based upon the alloy. That's a little different. But like if you're out there and you're finding portholes and something like that, and then you're gonna go back and you're gonna do some calculations, and you guys are gonna, maybe do some calculations, and then you just grab some lift bags and you're gonna go out there and just hook them up and like put air in until they're neutral. That's really what's gonna happen,
Okay.
But the idea of this just kind of give you a ballpark of how much you're gonna need when like 4 cubic feet, 5 cubic feet, to lift 300 pounds, that's a lot. That's not that much air to lift a lot of weight. You know what I mean?
Yeah.
So, but you also have to consider if it's stuck in mud and things like that. Something may only weigh like 300 pounds, but it might be stuck in some pretty dense mud, and you're not considering that suction strength there. So there's no way to calculate that. So it's just put lift bags on it and pull until it breaks free, and then be ready to pull that dump when it pulls free, or get out of the way. Because if something starts going to the surface, you don't want to be attached to it, and you don't want to be under it. So
Gotcha. Okay.
yeah, I think you were there when we floated the anchor last Sunday. I made it like nice and neutral, and we just kind of came up the anchor line, and then I was like, all right, time to pull it up, and I pulled it up, and it just started floating up. I did that on purpose, so anyway. All right, we only have 10 minutes left on this. I don't know how that worked, but we'll start going through the PowerPoint, and then when it cuts us off, we'll move over to Google Share or Google Meets, and then we'll go through the exercise then. Sound good, everybody?
Yep.
All right. Close, minimize this thing. I have to go to the right. I thought I had it open, but I guess I did not. It's right here. There it is. Okay. And now I need to. All right. There. Now I should be able to share it. I want to share this one. Okay, what can you guys see now?
Archimedes principle, buoyancy calculations to achieve neutral buoyancy.
Awesome. So we just went through all this stuff. Okay. So I guess I got more. All right, so 1 atmosphere is 1 bar or 33 feet of salt water. They're all one way to talk about pressure, right? When your depth on your computers and stuff like that read out in depth, they're just pressure sensors that are calibrated in depth. They're reading out. They're just little transducers inside there that read out pressure, but they're just calibrated, like I said, in depth. So so when people are talking about bar, they're talking about 1 atmosphere. All right, so there's difference between gauge pressure and that kind of stuff. So gauge pressure is what you see on your gauge, right? It usually takes into consideration atmospheric pressure. So if you took your gauge, or if you had like a pressure gauge in outer space, you took it to outer space, it would read -32 or -1 atmospheres, or -33 feet on your computer, or maybe it would say error or something like that. But it's already calibrated for 1 atmospheric pressure. So just take that into consideration. And then if you were to go to meeting controls, and if you were to go to atmospheric pressure, it would go back to 1 atmosphere. That's different between gauge pressure and absolute pressure. Absolute pressure is what it is. Absolutely, if you were to calibrate a pressure gauge in outer space where there's absolutely 0 pressure, and then you took it down to the surface, then you would have, you know, it would say 1 atmosphere. Can you guys see the whiteboard, or you still see the
Yeah, see the whiteboard.
see the
Yeah.
whiteboard? Great. Awesome. Okay, so I'm gonna make
Is that the same thing though? Like if you went down to like 100 feet, which is what, 4
4 atmospheres.
atmospheres,
Or yeah, 4
and then you calibrated something there and then brought it to the surface, it would be the reverse.
yeah, that's
Because
right.
you got the vacuum.
That's absolutely right. I can make
Okay.
regular lines. Do that. Bloop. Make some axes here. All right, so the depth equation. There's lots of ways that people can bring up the depth equation. And I'll show you like depth equation, EQUA equation. Let me see if I could find the really confusing one on the Google machine. And I'll show you why it's confusing. Images. Water depth. I'll put in water depth. Water depth equation. Anybody using a really confusing one?
I like your original one where you do all the depths. And you do 1 ATA, 2 ATA, 3 ATA, what you taught us in the
open water or the nitrox one.
yeah.
No, you know,
That made it very simple to me.
Well, if you were to plot depth, right? So here's your seawater. I'll make my squiggly line. I probably showed you this before, Zach, already, but bear with me. Here's your seawater, right? And if you were to plot pressure depth over pressure. Pressure goes up. You go that way because depth, higher pressure is that way. It's a little backwards because I wanted to match depth too. It would be like this, and then like that. All right. With your starting number being at 1, and then 2, 3, 4. I'm gonna put 5 right here. All right, why is this 1? Why is my starting number 1 and not 0?
Because you're at 1 atmosphere at surface temp.
Yeah, because I have the atmosphere. I have like the ozone layer up here, right, and all the weight of the air.
Right, pushes down at you at 1 atmosphere.
Yeah, in 1 atmosphere, weighs the same amount as 33 feet of salt water does.
Right.
Or 1 atmosphere.
And if you go above the stratosphere,
or,
you're at negative.
Yeah, if I go out in outer space or 1 bar or whatever, you know, all this stuff weighs the same. All that air weighs all the same, right? Right, and then every 33 feet, I go to another 2 atmospheres, so 60s, or so this would be 33,
66,
66,
99,
99,
120.
and 130-ish.
Yeah.
129, but we'll do 130-ish. Okay, and recognize that here's the bottom of the recreational limits right here. That's even the contingency limit. Right, so that's pretty easy.